Let us pause the theoretical development for a little bit and do an exercise. So I want to really study this ring, z adjoint square root of minus 5. Means all integers of the form, all complex numbers of the form a plus b square root of minus 5, where a and b are integers. Okay, all these dots that you see on the picture on the right hand side. Here is 1 and here is square root of minus 5, and you take all integer linear combinations of these two. So you get this square, this rectangular grid in complex plane. And this is a ring under addition and multiplication of complex numbers that you can check rather easily. What I want to focus on is this ideal I generated by 2 and 1 plus square root of minus 5, generated by this complex number and that complex number. And I want to show that R mod I is Z mod 2Z, that it's not a principal ideal, etc. This is some somewhat non-trivial computation, and it's also a good example to study because this is a prime example of non-unique factorization domain. So for many counter examples, it's good to keep in mind. I have a preparatory statement up here first, which I'll just leave as an exercise, which says that if you have two ideals I and j in a commutative ring R with 1, and I is generated by a bunch of elements x1, x2, xm, and j is generated by a bunch of elements y1, y2, yn, then the product ideal I times j is generated by pairwise products of the generators. So pairwise products of the form xi times yj, where I runs from 1 to m, j runs from 1 to n. And this is sort of immediate once you know what ij means. Ij means ij is the smallest ideal that contains all products of the form x times y, where x came from I and y came from j. And more explicitly, we saw that it consists of all expressions of the form a1, b1 plus a2, b2 plus ak, bk, where the a's are from I and the b's are from j. And once you know that, this one is immediate. Let's move on to the real exercise here. Part A is just some preparation to play with this ideal. Let's go through it nonetheless. It says you have this ideal generated by 2 and 1 plus square root of minus 5, and look at the ideal generated by 2 and 1 minus square root of minus 5. First thing, check they're the same. How do you check these are the same? Well, you show that the generators of I are in j and the generators of j are in I. So then it would show that I is a subset of j and j is a subset of I. So note that 2 is certainly in j because 2 is in both. And what about this guy? Why is this in j? Well, this guy is 2 minus 1 minus square root of minus 5. And both 2 and 1 minus square root of minus 5 is in j. So the difference is also in j. So both generators of I are in j. So I is a subset of j. Similarly, you check j is a subset of I. So I equals j. So I square is now I times j. And by the previous exercise, I times j is generated by pairwise products of generators of I and generators of j. So 2 times 2, 4, 2 times 1 minus square root of minus 5, so 2 minus 2 times square root of minus 5, and then 2 times 1 plus square root of 5, and then 1 plus square root of minus 5 times 1 minus square root of minus 5. That happens to be 1 plus 5, 6. Okay. And I notice that all these 4 complex numbers are in 2R. Because, for example, 2 times 2 minus, this is 2 times 1 minus square root of 5, and this is an element of R, so this is in 2R. Similarly, all 4 are. So this is a subset of 2R then. All those 4 complex numbers you see are multiples of 2 in R. Conversely, 2 is 6 minus 4. And 6 and 4 are both in ij, so 6 minus 4 is in ij. So if 2 is in ij, ij is an ideal, then any multiple of 2 is also in ij. So I have both inclusions, so I get ij equals to r. That's part A. Okay. And then part B, actually, so I want to show that R mod I is Z mod 2Z. You can actually prove it using part A, and I have sketched out a proof. Basically, what you show is that you have the ideal R, you have the ideal I, and now you have the ideal I square, which is 2R by part A. And you show that R is not equal to I, and I is not equal to I square. So both these quotients are non-trivial. On the other hand, you show that this quotient, which is just R mod 2R, has size 4. And that's basically because R as an additive group is just Z2, Z square. So this is just Z square mod 2 Z square, which is isomorphic to Z mod 2 cross Z mod 2 as an additive group, forgetting the multiplication, which certainly has size 4. So what we have is that this big quotient has size 4, whereas the small quotients both are non-trivial. But the size of this quotient times the size of this quotient amounts to 4 by third isomorphism theorem or something. So both of these have to be 2 and 2. Meaning the index here and the index here multiplies to 4, and they're both not 1, so it has to be 2 and 2. That tells you I is index 2, so R mod I has to be Z mod 2Z. But I want to give maybe the different proof now. This one is written out in the notes. One way to identify a quotient, you remember, is to write down a homomorphism from R to Z mod 2Z. So let's define that. Alpha from R to Z mod 2Z by alpha of a plus b square root of minus 5 equals a plus b mod 2. The image of a plus b in 2Z. Show this is a surjective ring homomorphism. That alpha is a surjective ring homomorphism, and that its kernel is equal to you guessed it, I. So if I know part D, then by first isomorphism theorem I'll know that the domain mod the kernel R mod I is isomorphic to the image Z mod 2Z. So D would imply B if I can prove D. And once you know that R mod I is Z mod 2Z, you know that Z mod 2Z is a field, so I would be maximal. That's how you recognize a maximal ideal, right? When you quotient by it, you should get a field. So I would be maximal. Once you know that I is maximal, you know maximal ideals are prime. So that would give you part B. So let's just check that alpha is a surjective ring homomorphism. So I have to check that alpha of a plus b square root of minus 5 plus c plus square root of d square root of minus 5 is equal to alpha of the first thing plus alpha of the second thing. And this is just straightforward. This would be a plus b plus c plus d mod 2, and this would be a plus b mod 2, and this would be c plus d mod 2, and this plus this in z mod 2z is certainly that. Yeah. So the addition is very clear. What about the multiplication? Let's verify that. Alpha of, so you take two things from R, right? a plus b squared. And so a, b, c, d are integers. And I want to check that this is equal to alpha of the first thing times alpha of the second thing. What is this? We have to multiply these numbers, so you get ac minus 4bd, or no, sorry, ac minus 5bd, I suppose, plus ad plus bc times square root of minus 5. So that's, oops, ac minus 5bd plus ad plus bc, the coset of that mod 2. On the other hand, if you did the other one, alpha of, or maybe we can just continue. This is same as AC plus BD plus AD plus BC plus 2Z, because what I changed by is 6BD, and that's certainly in 2Z. Okay, so changed by an even number, so they are congruent mod 2, but that's same as A plus B times C plus D. That's why I did this anyway. And this is same as A plus B plus 2Z times C plus D plus 2Z, okay, which is alpha of the first number then alpha of the second number. And now I want to check. So alpha is a homomorphism. It's surjective, that's clear. You just take 1, it maps to 1. And z mod 2z has only two things, 0 and 1. The kernel has to be I. Yeah? So what's the kernel? Kernel consists of, by definition, it's all these guys in R such that A plus B is 0 mod 2. And you check, certainly 2 is in the kernel of alpha, right? Because the real part plus, it's 2 plus 0 times square root of minus 5. 2 plus 0 is 2. And then also 1 plus square root of minus 5 is also in kernel of alpha, because this is 1 plus 1 times that. 1 plus 1 is 2. Conversely, if you give me something in kernel of alpha, then what do I know? I know A and B are integers such that A plus B is even. Then I can write it like this. It's the same thing. I've just done a minus B and a plus B. And then I can also pull out a 2.5. You see, because A plus B is even, A minus B is also even. So this is an integer, this is an integer. So I've written it as something times 2 plus something times 1 plus square root of minus 5, only with integer coefficients, and integers are certainly in R. So these are in R. So that shows that this, any such number is in I. So I is the kernel of alpha. Okay, that proves part D. What it tells in picture is that the ideal consists of these points. There's 2, there's 1 plus square root of minus 5, this one, this checkerboard lattice. And once you know that, you can actually see directly that it's the quotient is z mod 2z. So this green thing is the ideal I. Okay, and part C, maybe I'll just let you look in the notes.